Good day, welcome to this video. In this video, I'm going to be talking about how to implement an average current mode control routine in a microcontroller, how one would go about doing that. But in this case, I'm using specifically a PIC24FJ64G8002 because I'm able to do a spice analysis on this particular microcontroller and use it with MCC simultaneously. Um, so that's a good thing. Well, not quite simultaneously, but I'm able to generate the initialization code with this and do a spice analysis on it in Proteus. So it's a very good microcontroller to test sort of these algorithms, etc. This code routines rather. Um, so that's what this video is about specifically. Just the coding aspect. On how to exactly go about that in your code. So this is an average current mode control, which means uh we're using two sensors at the same time. The current and the voltage sensor, we're using both of them at the same time. So the major advantage of this particular routine is basically you have inherent current limiting. It's an inherent current limiting feature there because you're constantly sensing the current of the inductor and you never go past it. So in essence, you basically protect your switches. You protect a lot of things. From blowing up essentially in your microcontroller, which is most certainly a good thing, um, because there's an inherent current limiting feature there. Um, so you have two loops in this particular control. You have the outer voltage loop and the inner current loop, and sometimes it might seem quite confusing to implement this, but you kind of just have to do things step by step. So obviously this particular the performance of the system will be much better on a DSP, on a digital signal processor. This microcontroller is not made specifically for digital power supply needs, but it does work out. Obviously, it's not the maximum performing one due to the PWM resolution, but it works just fine, especially for this actually average current mode control. It works just fine. Well, in the simulation anyway, but in terms of coding a microcontroller and implementing it, the simulation is not that far off from the real thing because it's all mathematical essentially. In the simulation, in the actual microcontroller, it's all math essentially. It's all ones and zeros, so it's a lot more consistent in that way. Um, so I'm just gonna just do a brief overview of the code. So the code is essentially just this part here is just the initialization of the variables, the vref, the iref. The iActual is the for the measured current, vActual for the measured voltage, and this right here the control. I'm actually not sure I'm using this in this particular example, but I'm just gonna leave it there. Just why not? And here you have the voltage error array. Voltage error array, the voltage PID output array, and the same current error array, and the current PID output array. So this is for the PID control for both of them. More like PI control actually, it's actually not PID. And this V loop count is for the voltage loop. So the voltage loop is essentially 20 times slower than the current loop. So this V loop count helps us keep track of that. And next, there's basically nothing in the main loop. This I just put there for testing purposes, but it's not useful in this particular example. This phase shift, that's for something else. It's not useful for this particular example. So as you can see, everything's empty and sort of just simple and clean. And the actual loop is in the timer 1. And obviously here there's a timer 2, which is used for the PWM, and it's a 10. I'm using 100 kilohertz for this particular example, and that's why the PR2, the maximum. Okay, I should zoom in there. So the maximum PWM value is 159 max PWM, and this is timer 1. This is where the actual code is at, and yeah, so that's it. So this is the actual code, so I'm just gonna go through it. So first off, you wanna get the sensor readings, and so for this particular part here, so you have the so this is for the voltage sensor. This area here is for the voltage sensor, and let me just put a space there. And this is for the current sensor, right? And the current sensor is a Hall effect one, ACS 712, in this particular example anyway. But the voltage is just a simple resistor divider, right? So the big resistor is 1.2 mega ohms. The small resistor is 220 kilo ohms, which is quite small, but we're dealing with smaller voltages, so it's fine. You can make I guess the resistance relatively small, but 20k is relatively small. When you're talking about sensorized, because you want your sensor to be high resistance, high impedance, so it does not affect your efficiency essentially. So it's good to make your sensor resistors using to sense your voltage as high as possible. Um, so that's that. So this is how you calculate it eventually, essentially. So 5.0 is the VREF for this particular example, and the ADC 1023. So this is essentially 2 to the power of 10 minus 1. Okay, so it's a 10-bit ADC, that's why this value is there. So essentially what this line does, it converts whatever it sees on the sensor pin, it converts that to an actual real world voltage, tries to get what is the actual voltage of that value. So once it gets that, it has to scale that back up, because remember there's a resistor divider on the particular pin. So it has to scale that back up. So that's what the next line is for, this particular line. So let me just show it. So this is the resistor divider. So as you can see, the first one is 1200K, which is 1.2 mega ohms, and the second one is 20K. So it has to scale that back up. And if you do this calculation, you essentially get this value here. So if you say 5 divided by 1023, multiply by this here, this sensor gain value, I guess, this is the value you get. So I'm not including these two lines here for obviously because for the microcontroller to be quicker, you know, in calculating, so we just use a single one. But it's put here for the comments for to be modified essentially based on your resistor value. So obviously the top resistor 1200K is going to be this value right here. The small resistor 20K is going to be this value right here. Obviously didn't write 20,000 because space, I guess. So it just said 1200 2020, same. Um so that's what these two lines are for, and this is what you get in the end. So there you go. And for the I actual, the exact same thing. The first step, you convert to an actual real world voltage, and then right after that, you obtain it based on this formula. So for that particular sensor, let me just go to it. So this particular sensor, in this configuration, the way it is, so you're gonna have to take a closer look at your sensor board if you're using this particular one, ACS 712 20 amp variant. You have to take a look at it and connect it in this configuration, I guess, because in this particular configuration, right, whatever voltage you sense, the more the current flowing through it, the lesser the voltage on this pin is, the VI out. So as a baseline, there's a voltage offset of 2.5. Sometimes it's not 2.5. Just make sure you sense that and actually look at that with an oscilloscope. Don't use a multimeter for that to get this baseline value. Use an oscilloscope because an oscilloscope will show you most likely what your microcontroller is also going to see. So once you look at it through an oscilloscope, the accuracy of an oscilloscope is a bit compromised according to the leads you're using, but I still think it's a little bit better than using a microcontroller, sorry, a multimeter, because the multimeter sort of just averages that value out. So, whichever one you use, you can actually just use 2.5. I guess it's your choice. You could use either one, multimeter or oscilloscope. Me personally, I like to use both, the multimeter to get a baseline and the oscilloscope to get closer, I guess. Um, but you could just assume that it's 2.5, that value is 2.5, right? And if you connect it in this particular configuration, then the voltage is gonna the voltage on the output is actually gonna go lower the more current is flowing through. And if you connect it the other way, the opposite is gonna happen. For those that are using MCUs, microcontrollers that have a VREF of 3.3, I recommend connecting it like this, because then you're sure it's never gonna go above 2.5. But if your microcontroller goes up to 5 volts, then you can connect it however you want. Obviously, this equation will not apply to you. You're going to have to say whatever value you get minus 2.5. But I don't like that. I prefer it this way because it's safer essentially. You limit what goes into your microcontroller to 2.5. It's never going to go over 2.5 with this particular situation you have here. And sometimes in the end you might wanna do an absolute value FABS to ensure that it doesn't go you don't get a negative reading on it. In this case, because I'm simulating, it's never gonna go below 0, but in the real world there's noise, etc., so it might go below 0. So you don't want to be sensing minus something in your sensors. You want to sense 0 for the sake of your PID control loop anyway. So that's that for the current sensing. And obviously I do everything in one line because you know, I don't want to waste time essentially. And this 0.1, so for the 20 amp variant it's 100 millivolts, 100 millivolts per amp, so that's why this is 0.1 over here. For the 30 amp variant it's 0.66 millivolts, so this would be 0.66, but this is the 20 amp, so leave it at 1. But adjust accordingly, and then you would get this final equation down here. Obviously this is 2.5 divided by 0.1, and then this value is a bit more, is it complicated? No, I don't think so. So this value here, you get it by just saying 5 divided by 1023 multiplied by this. Wait a minute. No, divided by 0.1 rather. Sorry about that. Divided by 0.1. Um, Let me actually confirm that very quickly. Yes, that's what you do. So you say 5 divided by 1023 divided by that value divided by 0.1, and you get this value. Or if that's too much, just comment this out. Comment this out and uncomment this. You can do this as well. Keep in mind it's gonna take a little bit more time, but who cares? At least you get the correct current value all the time. Alright, but personally I just leave this. Anyway, so that's that. So now you're into the current loop. So essentially I'm using a velocity form PID. Um Velocity form PID controller because it works. I find it works better for power for control of DC-DC converters. It works much better than the position form. The normal form, the familiar form is the position form. Um, Widely used in a variety of applications, but I find for this one specifically, for me anyway, this works much better. Um, so this is it. So I'm gonna put a link for a document you can read about this, about how they formulate this. I'm not gonna get into that, but this is the equation that you use. So that you have the Kp, Ki, Kd multiplied by the original error. And yeah, before that, okay, let me just finish that. For the original error and minus the Kp plus 2 times the Kd. It looks kind of weird because like it's like where's this 2 coming from? But if you read that document, everything will be explained in it. So just check that out. And you have the error, the previous error, and then you do the previous error. And I guess that's the downside of this. You have the previous error. You have to keep track of 2 previous error values, but that's fine, as you could just use this. So this is the previous PID output. You equate it to the current PID output, and then you have the the second one, two errors ago essentially to the past error, and the past error to the current error, and obviously you update the current error with this equation right here, and then you update the PID, right? And then after that, this is programmed to have a maximum. So the maximum value here is going to be 0. I think it's 0.8. It's stated up here. So this has 0.8, which is 80% duty cycle essentially. Um, so this is coded in such a way that the maximum that this is gonna give is 1, right? Because if you look down here anyway, so this is the limiting the PID value. So after that, max duty. So the max duty is 159 in this particular case for 100% duty cycle, and this value, the maximum is 1. It's always going to be 1. Well, in this particular case, it's 0.8 because it's limited, so it's going to be 0.8. So the maximum duty cycle is going to be 80%. You might want to reduce that to 75, 65, whatever, because I don't think converters act very well efficiency-wise at high duty cycles in generally. So you want to limit that to something decent, depending on what you calculated, etc. Your theoretical values. But that's essentially what this is. And the reason why that's limited to 1, um, this value is limited to 1, is because when you're doing the PID control calculations mathematically, you're already assuming that the maximum output is 1. You're not assuming it's 100 or whatever your microcontroller gives. So it's better to work on that principle and then scale it when you get to your microcontroller. When you get into coding it on a microcontroller, and you're essentially scaling it by multiplying it by the max duty, by scaling it to actually what your microcontroller sees, right? So for your microcontroller, 100% duty is 159. But based on your calculations before you're actually plugging it into the microcontroller, it's you're basing your calculations on the fact that the maximum duty is 1. Usually, from all the calculations that I've seen in textbooks, that's all they do. They base it on that the maximum duty is 1. So you have your 1 there, and then you have the max duty of the actual microcontroller, what it actually sees, which is in this case 159. And if you migrate this code into another MCU, all you literally have to change is that max duty. You won't have to go changing the coefficient. Well, as long as your sampling time stays the same, you won't have to go changing the coefficients again. You just, change this particular value, which is much better than having to change coefficients every time you jump in from one microcontroller to another, which is certainly impossible if you're not getting the right things from it. All right, so that's that. So that's the inner loop. So for this particular example, this loop occurs every 130 microseconds. Every 130 microseconds. That seems small, but it's actually quite alright. It's actually supposed to be a lot less than that, but this microcontroller is quite limited in terms of what it could do, so that's why it's that value. Anyway, so that's the max duty. So that's the inner loop. So now you go to the outer loop. Let me just comment that out. So this is the outer loop. So the outer loop has to be 20 times slower than the inner loop. Well, not 20 times, actually 10 times. I just prefer to make it 20 times because I like to give the inner loop a lot more time to actually get to the set point before changing it again by the outer loop, changing the set point with the outer loop. So what the outer loop does is it determines this particular set point. So this is the IREF, reference current. So the outer, and as you can see here, the PID output here is PWM directly, goes directly to the PWM and changes the duty cycle. Whilst with the outer loop, it's a bit more interesting, right? So the output, PID output of the outer loop becomes the IREF, as you can see there. Obviously, it's scaled as well because the maximum value, the actual maximum value of the outer loop also has been limited to 1, as you can see here, not 0.8, because this isn't directly affecting the duty cycle, so we can make the maximum here 1, whilst this one has to be 0.8 because it's affecting the duty cycle. This can be 1, but there's also a value here called the max current. So what do you want the max current of this guy to be? You want to limit that. So remember I talked about an inherent current limiting feature. So this is it. So the max current in this case is if you look up here, it's defined as 12 amps. So it's never gonna go above 12 amps. So in essence, you're basically protecting your MOSFETs, because that's one of the major issues with average current mode control, is that the set point, um this you often the issue is like blowing up switches because of the set point issue. So sometimes how do you say it, or let me say rather just regular control, sometimes the set point for the inductor is like just way too much. The current flowing through the inductor is crazy. It's going up and down. It's kind of weird, and that affects the MOSFET, because basically the MOSFET is in a direct path. So the current flowing through the inductor flows to the MOSFET, and it could blow it up essentially, um, ruin the MOSFET. But with this inherent current limiting feature, now you ensure the maximum current that's gonna be flowing through the MOSFET is 12 amps, not more than that. It's always gonna be 12 amps, which is definitely a good thing. Um, So that's what that is. So this is the outer loop, exact same as the inner loop in terms of the structure, but the output, the PID output, now links to the IREF, and not directly obviously, because the maximum value it can give is 1. So you have to scale that to the max current, which is 12 in this case. You want the max current in this case to be 12. Obviously for your various applications you want to increase or decrease that, but in this case it's 12. So that's what this code is essentially. And obviously this, I don't think this is necessary. That's just to sort of see what's going on with it, to sort of debug. Maybe I should leave that there actually. Should leave that there for those of you who want to debug. Just keep in mind to actually use this, we have to connect your ART pin to RP15, and for those that want to use this particular microcontroller, um and yeah, I think that's about it. That's it. All right, what's next? Yeah, okay, let me just see this highway max client. And what else? What am I missing? Yes, to actually make this work, it's important to do this, right? So you wanna disable the outer loop first. You don't want to test both loops at the same time. You want to disable the outer loop, which you do by just making vloop count equals to 0, because that's what this does. This does the plus plus, and then once it's 20, it executes the loop, makes it 0 before it actually starts executing the loop. But you want to make the vloop count 0 first, and then equate that to 0 to actually disable the whole thing, and test this independently, right? So in the main part, I set the IRF to 1.5. Let me change that to 3.5. And so if you go to timer 1, so there's a couple of pointers I put up here and how to choose your coefficient. Okay, I haven't. Let me do that now. Um, to choose your coefficient, some basic rules anyway to choose your coefficient. It's a thumb suck rule. Um, so essentially you want to start with a KP of this and a KI of this as low as possible, essentially. And then ramp it up slowly. So you want to keep a relationship between them such that KP is that KP is at least 3.5 multiplied by KI. You want to keep that change there, and to make it faster, you want to increase the KI value. Whilst you increase the KI, and then you have to increase the KP as well to keep that relationship there. KP equals to 3.5 multiplied by KI at least. and eventually it might go unstable, so you want to take down the KP, and then you change the relationship to 2 multiplied by KI, but you still increase the KI because you're trying to make it faster. You're trying to get your system to get to the settling point much faster, essentially. So that's the general rule for this. And what you're concerned with, because we're testing the inner loop now, so you just KP, KI. So this is what you want to be concerned with. Obviously, I've fiddled with it already, and that's what you want to check first. So you just go here in the spice analysis and go check that. Obviously, you're gonna be checking on your actual system. And one thing to note with the hardware, for average current mode control, it's your inductors in CCM constantly. So for your inductor to be in CCM, you have to ensure that your this guy is sufficiently large, right? So um you can't have 60 microhenries here. This is not like constant voltage on the output only. You're monitoring the current as well, so you can't have like something like 60 micros unless your frequency is so high. Your switching frequency is like really high, which is not in this case. It's 100 kilohertz, so you kind of have to increase this value here to 700 micro. It seems like a lot. It's a lot actually, but well, CCM. So there you go. Obviously there are calculations to be done, but for this example, I prefer to just use a sufficiently large value to ensure that the code operates properly. Obviously, in your particular applications, you might require lesser value for this. Um, what you want to be concerned about is your output capacitance. You don't want this to be too large. 100 microfarads for 100 kilohertz is sufficiently large enough, so you don't want to go too far up, too far higher than that. So that's that. All right. So let me just increase that. No, it's there, so I can just run it. So essentially, if you run the inner loop first, you can actually see what the issues are. Because if it's not settling to your set current, your IREF, then you shouldn't even bother to include the outer loop. You want to check the inner loop first and actually check that it's settling to the current that you need. And in a boost converter, that's easy to actually see. Um, so I'm just do this. All right, so that's approximately 3.5. So that's a good thing. Um, and it does it relatively quickly. So, oh, let's say relatively. That's 7 milliseconds. All right, so that's good, I guess. Just see that it's 7.9. There's a bit of an overshoot, but that's fine. I think your inductor can take that. And it's a fast loop, so you expect that anyway. So that's a good thing. And if that's not the case, if it's unstable, if it's super unstable, then obviously you have to start from this. You have to change the KP to that value, the KI to that value, and then increase slowly to see exactly what the point is. And to be honest, oh yeah, I wanted to say this would not work for a buck converter, but it actually will, because the current flowing through your inductor for a buck is also continuous, so it will be fine with a buck as well. Yeah. So that's that. So after you've confirmed that it's working just fine, then what you do is you can uncomment this and include the outer loop, the outer loop voltage. And also with the outer loop voltage, you want to start with, when you're just including it for the first time, you want to make it as slow as possible. You don't want to make it fast. So how do you do that? At first you increase slowly as you do, and so you do that. You change the value. You change the KP to this value. You change the KI to that value. Um, change the Ki to that value. Yeah, and then you ramp up slowly, because now you've confirmed that the inner loop works, so you kind of don't want to ruin it with the outer loop. So that's how you do that. And now that has been done, you just run the code again. Compile the code. And now at this point, the voltage set point is set to 35.0. And obviously, if you increase this VREF, you increase that, eventually, the amount of current that has to come in your input will go above 12. So you have to adjust your 12 accordingly. And your control max, this is a simulation, so I made this 0.8, but you might want to change this to 0.65. I don't know. You might want to do that or make it less. But this is simulation, so there's nothing really at risk here. And the max duty, obviously, for the other different types of microcontrollers, TI, STM, Renaissance, etc. You want to change this value. Right. So just run everything again. Right. Compile rather. And just change that. Delete. And now I'm monitoring the output voltage. And obviously, let me just run that. And obviously, also, obviously, I'll make the code is available. You can click the GitHub link in the description and get access to the code. You can play with it. Keep in mind the code is essentially just to show, unless you're going to be using this particular microcontroller, this one specifically, the code in this case, you can't really run it directly on your microcontroller. Well, how do you say it? Well, it does show a step by step on how to accomplish average current mode control. Well, this code exactly the way it is, if you're going to run it on this microcontroller with this exact same type of converter, obviously it will work as it is with this, everything the same. It will function appropriately, but if you're not using this particular system, you might want to just sort of try to use this as sort of like I guess a way to do it, essentially, or a template, I guess, because the PID code always stays essentially the same. It doesn't change. It's always going to look like this. So that's that. Let me just go there. Yeah, there you go. It's 35. As you can see, it's jumping up and down a bit when you zoom into it, but remember, this controller does not have a great PWM resolution. As you can see, for 100 kilohertz, it's 159, which is not a great PWM resolution. So you see, it goes like that and it jumps. Obviously, you can tweak with this with the coefficients, etc., and make it a bit better. So the minimum here is 34.5, maximum is about 35.3. Yeah. There you go. And that's that. And yeah, with average current mode control, especially when we're dealing with fast loop times, you don't want your capacitor to be too large. Try to keep it low, because even when you calculate it, when you actually calculate the capacitance required, it's usually not large. It's usually not large. It's about 3 microfarads or something like that, or 5 microfarads if it's quite high. Just go a bit above that. If you can get away with using polyester capacitors, do that. Or if you're gonna use electrolytic, at least use one polyester with it in parallel with it. Right? Am I saying the right thing with polyester? Non-electrolytic. Let me just stick to non-electrolytic. So you want to use capacitor like this, which is electrolytic, and you want to use non-electrolytics in parallel with it, because it helps a lot with the resistance, the parasitic resistance issue, and it gives you a much smoother voltage on the output, like a lot smoother if you actually use them together. and you don't want them to exceed 100 microfarads, especially for such a high frequency like 100 kilohertz. 100 kilohertz is not super high, but it's, you know, it's reasonably a high frequency where you could use it and get away with using conservative values for an inductor and a capacitor. Obviously here it's a 700 micro, it's not so conservative, but you are running it in CCM, so it's better that it's a little bit larger than required than, you know, lower. Because, okay, let me give you an example. Let's say this was 60. Now let's see what the output voltage would look like. If it will actually get to the set point. Um, okay. Seems like it's taking time, but it's actually relatively fast for this software. As you can see, it's not so good. It's not so good. I mean, it's trying its best to get to stay at 35, but you know, because the inductor is not, the current going through the inductor is not so, how do I say, it's not so stable. So you can see this is going up and down, and it's allegedly supposed to be 35, but sometimes it actually goes up to 50, and you see it's trying its best. But you know, better to keep it high. Just better to keep it high, and then you won't have any problems with your with getting to the set point. Right, so here you can change that. If you really need to change that, you can try 43.0. Yeah, let's go back there. Okay, you can see it's back to normal. So now I just want to change the set point again of the UF, and obviously this IRF obviously is going to discard of it after the first iteration. This is sort of to get the system started from zero. You don't want to start it necessarily at zero, the IRF. You want to get it started somewhere in, you know, 1.5 is a good place for an inductor to start. And obviously if your requirements are much, and if your requirements for your boost converters like really low voltages, then I don't really think you need CCM, to be honest. You could just do it with one loop, one voltage loop, or just one output current loop. And obviously you change the positioning of your currents to over here, current controller to be here, not where it's at now, but you know, there you go. So you make your V-Rave 43.0, change this to something stable. Um, so now the set point is 43.0. Um, just go back to, it's almost done. As you can see, now it's at 42.9. Just fluctuates there. Now, obviously, if you use a microcontroller with a better PWM resolution, it will be much better. It won't be going kind of haywire like this, but it does get to the set point. That's the most important thing, and it stays there more or less on the set point value. So that's essentially how you do an average current mode control with a microcontroller. This is how you code the routine, and obviously ADC for those who want to use this microcontroller. ADC, ADC1, OC1, PWM, timer 1, 130 microseconds. Seems like it's really fast, but it's actually just okay. And you have timer 2, which is 10 microseconds, 100 kilohertz. And there you go. There you go. And this is the code. This is the outer loop. It's the exact same thing as the inner loop. It's the exact same as the inner loop. Only difference. Um, Only difference is the output here directly affects the PWM OC1RS, and the inner one just changes the IREF, changes the reference or the max current as well. And if you're having instability issues, disable the outer loop, work from the inner loop, and sense that, and give yourself something on your hardware such that you can monitor the current going through the inductor independently. You can actually see what it is. Don't make everything so inline. You prototype anyway. Try to see that, okay, I can at least see what current is going through the inductor. And that's how you do that. And for instability issues, always start with these set values. KP 0.003 is super slow, right? Super slow, like slow. Control is so slow you can notice it trying to get to the set point. You can actually notice that, which is really slow control, especially for DC-DC converters. But it does get to the set point, gives yourself a stable baseline to go off from, which is a good thing. And yeah, and always start to the KP output, the outer loop, also coefficients from this point. You don't want to start. You don't want to make your inner loop unstable. You don't want to make your inner loop unstable, essentially. Um, if you've already proven it to be stable. All right, that's that, and that's it. That's it for this video. Guessing if you have specific questions regarding the code, you can ask. Um, you can ask them. Otherwise, that's it. All the best with your applications, with your various applications using this. Cheers. Bye.